All right, so let's finish up. I know that the notes are a little out of order here, but let's go back and let's talk about calculating energy changes with chemical reactions. So now we are going to kind of take our idea of moles and the relationship in a balanced chemical equation. We're going to add a little energy into it to kind of use that as a way to convert into different values. So it's important to remember before we get started that if a reaction is exothermic, then that means that energy is included on the right side or in the product side of the equation. If it's endothermic, that means energy is included on the left or the reactant side. So let us look at an example here. We're going to calculate the amount of energy released in kilojoules when we have 30 grams of ammonium bromide forming. So just like we've kind of seen before when we're talking about limiting reactant, we have 30 grams of ammonium bromide forming. And it says that in this reaction, just by looking at it, that we are releasing energy, right? So let's interpret this value here. This value here means that we are exothermic, right? Because the energy is located on the right side of the equation. And it also is relative to this equation. It's really important to understand that. What that's saying is that relative to this equation, we are releasing 188.32 kilojoules of moles. If we were to increase the amount of stuff that's on the reactant side, say increase the number of moles, then the energy would go up. But we're talking about in this equation, for every 1 mole of ammonia that reacts with every 1 mole of HBr, we get 188.32 kilojoules of energy when every 1 mole of NH4Br is formed. In this situation, it is expressed in grams. So the reason why I keep saying moles is because it's important to be able to relate those two things together. So let's first start by converting into moles. I'm going to take those grams that were given to me, that's ammonium bromide, and I'm going to convert those into moles. Nothing special, this is just molar mass like it always is. The molar mass of ammonium bromide is 98 grams, so that's ammonium bromide. That's for every 1 mole of ammonium bromide. Now, we are going to convert this into moles, which we are doing so here. But now I want to convert it out of moles and into kilojoules. Now, like I said, this is based on kilojoules per the number of moles reacted in the problem. So for every 1 mole of NH4Br that reacts, we form 188.32 kilojoules of energy. That's how we interpret that number. And that number is based on the number of moles in the front. There is only 1 mole of NH4, so for every 1 mole of NH4, that's how much energy I release. If that number was different, then I would put a different number of moles in that conversion. So, if we take this and we go through the math real quick, we get 57.6 kilojoules. So again, that number that we have on the right there is related to the molar ratio in the balanced chemical equation. Let's check out another one. What mass of CrO3 reacts if 16 kilojoules of energy was released, according to the following equation? So in this situation, we are starting with kilojoules, and we are trying to convert kilojoules into grams, right? So let's give it a shot. We have 16 kilojoules, and we want to convert 16 kilojoules into moles of something in particular. We know that in this chemical equation we have 5.4 kilojoules available. That's the amount of energy that's involved. And it says that we are doing CrO3. So if we look at the balanced chemical equation, the CrO3 technically has a 1 in front of it. And this equation tells us that for every 1 mole of CrO3, we release 5.4 kilojoules of energy. And then we just kind of keep going. We're going to go out of moles of CrO3 because we're trying to get into grams of CrO3. The molar mass of CrO3, if you can believe it or not, is actually 100. As soon as I can learn how to draw a straight line. There we go. And when we get this answer, we actually get 296 grams. We got to be careful with our sig figs because we want to express this in 2 sig figs. So we are going to express it like so. All right, but again, that value in the equation is based on the amount of energy released per mole as seen in the balanced chemical equation. So you know that there's going to be a situation where it's not a 1-to-1-to-1, right? Let's check it out. One more example. This one's a little trickier because it's more similar to something that maybe like you'd see on a test. So this time we're looking for formula units, which remember are the same thing as molecules. And we are given we say that we have 95 kilojoules of energy. We're trying to produce that much energy. And the chemical equation is given. It says that based on that ratio that we see here, we are going to form 100.18 kilojoules of energy. But we're saying, how much do we need to use to only produce 95 kilojoules of energy? Why don't you give this one a try? Pause for a second, see if you can put it together. If you run into a common mistake, then keep an eye out for the solution, but pause and give it a shot. Hopefully this is what you got. If you got maybe less than this, I encourage you to look here. Notice that I wrote 2 moles of NABR. Why? Because again, this value is based on this current chemical reaction. We're saying that for every 2 moles of NABR that reacts, we produce 100.18 kilojoules of energy. So I have to reflect that in my balanced chemical equation. This is a little different than what we're used to seeing, but it has to do with the equation itself. So I take that, I cancel out my kilojoules by using the energy given, I cancel out my moles, the formula units is just good old Avogadro's number, and next thing you know, I have what I need, 1.14 times 10 to the 24th formula units of sodium bromide. Folks, that's it. Short and sweet. We will see you next time.